Hello students, welcome back. We just completed section 1, where we discussed the main idea of the definite integral associated to the signed area. And then we did some estimation problem as well. Now let's go to section 2. Here we're going to do some precise computation, not estimation by eyeballing the graph and counting the grid. We're going to do some precise computation here. For that, we're going to need a new tool. And that new tool is the Fundamental Theorem of Calculus. It's rather formidable, but let me try to break it down as much as possible. Let's begin with a continuous real function defined on a closed and bounded interval a to b, and let's name it lowercase f of x. So that's going to be the integrand. Then there is an antiderivative function, capital F. So capital F is also a real function defined in the same closed and bounded interval a to b, and then it is continuous, and then it is differentiable, and moreover, the derivative is the original function small f. See, capital F prime is small f, as I just highlighted in green. Now, here's the real deal. The integral computation, the definite integral of the original function, lowercase f of x, in the interval from a to b, is the net change of the antiderivative function, capital F. Capital F of b minus capital F of a. Now, there are more than one antiderivatives, but it's okay because they all differ by constant, and subtracting one from the other will kill off the constant. Let's discuss this through an example problem. Here's a simple example, and here's a visualization associated to that. Look at the graph, y equals to f of x, which is 1 minus x squared, this parabola, and then integrating from -1 to +1, so -1 here, +1 there, so the graph is above the x-axis all the way, so we are looking at this shaded region. In short, we are looking for this area. So how do you calculate this area? One way to do that is to find an antiderivative function and then doing this. Capital F of 1 minus capital F of -1. So here we go. Set this up as lowercase f of x, and let's look for the capital F of x. It's just antiderivative computation. You see? 1 becomes x, x squared becomes 1/3 x cubed. And please check, if you take the derivative of the right-hand side, you're going to get 1 minus x squared back. Okay, alright, we got an antiderivative function, and then we're going to calculate the net change. Capital F of 1 minus capital F of -1. So, here, plug in x equals to 1, plug in x equal to -1 and subtract 1 from the other, you're going to get 4/3. So, antiderivative computation, and then the net change of the antiderivative. Capital F of b minus capital F of a. Plug in b, plug in a, and then subtract 1 from the other. And please note that this plus c doesn't play any role, because they cancel each other out, the subtraction. So this plus c doesn't do anything. So if you just do without it, just remove it, that's going to be totally fine. But then again, this is a bit inefficient and there's too much writing here. So this is a standard way that I want you to follow. Calculate the antiderivative. You see, 1 minus x squared, this original function which I just highlighted in purple, became this antiderivative function which I just highlighted in green. 1 became x squared became 1/3 x cubed. Just following the antiderivative rule. and then apply the fundamental theorem. Plug in 1 and plug in -1, subtract one from the other. And that's just a computation. We ended up with 4/3 precisely, and that's the area here, 4/3. Well, let's do this several more times. How about this computation here? Okay, let's go ahead and do that. And this computation, this integral, requires some work. I cannot do the antiderivative computation directly, so let's break up. Let's FOIL it out inside. What do you have? First, 1 times 2, and then outside, t squared, and then inside, -2t, and then finally the last. Did I break up correctly? And then let's find out antiderivatives. 2 became 2t, t cubed divided by 3, and then t squared, 1/4 t to the 4th power. Did I do this right? Please check. And then -1, 2, +1. So how about the antiderivative? 2 became 2t, t squared became 1/3 t cubed, 2t became t squared, t cubed became 1/4 t to the 4th power. All good? Okay, alright, and then let's plug in +1 and -1, subtract one from the other. So let's copy and paste this entire thing. As a matter of fact, let's just copy and paste like this. And then plug in 1, 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 and then, excuse me, I shouldn't be plugging in -1, I should be plugging in zeros. Sorry about that. Okay, starting number is 0. So okay, alright. Copy and paste all those. And then I'm substituting 0 here. 0. So that's 0, and that's 0, and that's 0. As a matter of fact, all 0, so you don't really have to do this, but I just did it for argument's sake. And then if you do this computation, and just pick up your calculator and do your computation, I have Mathematica here, so let's do the computation. And it is 13/12. That's the kind of computation you can do. Let's see. What is this signed area here? So 1 minus t, 2 plus t squared. T is going from 0 to 1. Okay, it's like this, and then this area here, and it's clearly positive, apparently. Okay, it wasn't that interesting. Even without the picture, the computation is self-sufficient, so that'll do. By the way, this very same computation is in the answer key, so you can open up. I guess enough time for another exercise, so let's go ahead and do this. How about this? So please recall all the techniques that we went through for antiderivative or indefinite integral computation. Exactly the same thing applies there. So this thing could have been rewritten as 1/2 power. Please note that. And then you can separate the numerator, 3x minus 2. And then this one, 1/2 power, and that 2 is divided by 1/2 power. Let's copy and paste once again. And then that one here, number part is 3, and then x to the what power do you have? Nothing is up here, so 1 is hidden, and then 1/2, so 1 minus 1/2 positive 1/2 power. And number point is 2. Actually, what power here? It should be negative of 1/2 power. 0 minus 1/2. Okay, exactly the same as definite integral problem. Indefinite integral problem, excuse me. And then let's go ahead, find the antiderivative. 3 times x to the, let's see, add 1 to the power, 3/2, and then we have to divide. Simplifying, looks like you're going to get just 2 times x to the 3/2 power. Please check. And then the next one, 2 was there before. Add 1 to the power, so add 1, we have positive 1/2, and then divide. Simplifying, you're going to get 4. Please check. Is this the correct antiderivative computation? Or you can take the derivative and check. And then that's running from 1 to 9. Okay, plug in 9, we get 2, 9 to the 3/2 power, minus 4 times 9 to the 1/2 power. And then if you plug in 1, 2, and then 1 to the 3/2 power, minus 4, 1 to the 1/2 power, that's what you're going to get. Well, it's not too bad, because 9 to the 3/2 power, 9 to the 1/2 power is 3, 3 to the 3rd power, 27 times 2, so it's 54. And then this one, 4 times square root of 9, 3, 12. So you see, you can do all those computations. So punch in the calculator and you're going to get what you want. So that's 42. And then this thing is negative 2, so entire thing is going to be 44. Let's see, is that what I got here? 44, yes, that's the correct answer. And if you want to see the graph, you can go ahead and plot from 1 to 9 and do your computation, but I don't think that's really necessary. If you're interested in a graph, go ahead and plot yourself. We have one more problem here, and this one is going to be a bit more challenging because the integrand is complicated. Do you recall how to handle this? In the end, you have to plug in the top and plug in the bottom and subtract one from the other. But in order to do that, you have to manipulate this trigonometry. So cosine squared function can be rewritten as 1/2 plus 1/2 cosine of 2x, called power reduction identity, or double angle identity, or half angle identity, whatever you may call. And then what you want to do is antiderivative, and then plug in 0, plug in pi, subtract one from the other, and then you're going to get what you want. Well, stop the playback and go ahead. I gave you a sufficient here, a big hint here. Well, is that what you got? Power reduction identity, and then separating the numerator, we got that. Antiderivative, 1/2 became 1/2 x, and this one, cosine, became sine, and then we have to undo the chain rule, so we have 1/4. And then just apply the fundamental theorem. Plug in pi, plug in 0, subtract one from the other, and you're going to get the answer. Okay, so much for elementary exercises. We'll come back and do a little bit more exercises on the fundamental theorem. Stay tuned. See you soon.